I think this is where we were last time. So yeah, we could start.
Yeah, so just to summarize the previous classes, the summary was that so a simple database where you just set and get to the file system, write to the file system. The simplest use case is a log structured database where you only append. The only write supported is a append only action, and so the problem with that is at some point you would hit a so basically you are only appending. So we could optimize it because you are putting both keys and values in the same file. It kind of you will soon hit a limit where the file cannot be stored in memory anymore. So what we do there is we split the file in the database in such a way that we only store the keys in memory and values in the disk. So in the keys are pointing to the disk offset, and we kind of we have an easy lookup. So whenever a key is looked up, we know the disk offset, and we go fetch the value from the disk. Even with that, we hit a.
Where are the disk offsets stored in the memory?
In memory, along with the key.
Okay.
Yeah, in memory hash table.
Yeah. So even with that, we hit a limit that the number of keys that can be stored is limited by the memory, the in memory, whatever the limitation of the system. So so to work around that, we have we divide the keys into segments. So whenever we reach the limit at certain threshold, we start writing to a new segment and write the old segment to the disk. So now you have several. So now you are writing to the current segment, but then there is a risk of duplication among the segments. So you might be writing a new key. So remember, we are not editing the segment in any way. The rule about the log structured databases is that we only support appending and no editing in between. So now if let's say I wrote Vijay 1 in the previous segment and I wrote Vijay 2 in this segment, now I have to while reading, when I try to look up Vijay, the database basically fetches the most recent value, the one with the latest timestamp, and gives me the value, gives me the response. So so what we do there is, so in order to optimize this storage space, the older data is not relevant anymore, right? We are only always referring to the latest data. So to make the storage more efficient, we do something called compaction, which is deleting the duplicate keys from the older segments. And this is done as a background job. Like it picks up the segments and then kind of does this deduplication. So that's about the log structured databases, right? Anything to add there, or did I miss something? Yeah, and there are different ways of compaction. I think that's what. There's a size tiered compaction, and there is a layered compaction. The book doesn't go deep into them, but it's basically different algorithms to identify keys that can be removed, and how this merge happens also. So basically in the size tiered compaction, if you have a write pattern which is doing frequent writes, I think if it's a write heavy thing, then you don't want to wait until the segment becomes too big. You want to basically merge the smaller sized segments and kind of keep the merge operation small. If it's an infrequent write, then you would want to use a layered compaction technique where you wait until you wait until the segment grows large enough, so you don't have to frequently do the background merging. I think this is basically, it depends upon the write patterns you have. And I think Apache Cassandra, they follow this log structured data, basically the storage format. Did I miss anything? Vijay, anybody to add to that?
I think it's a pretty good summary. I think, yeah, he hit all the main points.
Yeah. Did we talk about a sorted string table last time? We did, right?
I think we got to it. Yeah. So.
Yeah. Yeah, so the two key, so right now, until now, we've just been, so the problem here is writes are, the main advantage of the log structure databases is that since it's always append only, the writes are super fast. The background job takes care of compaction, but the act of writing is super fast because it's only append only, right? You don't have to deal with any random seeks and all. So, but the problem with that is the reads are super inefficient now because the data is scattered all over the place. So to optimize that, the keys are, one optimization is that the keys can be stored in a sorted way. Then that becomes a sorted string table.
Right.
So that's called the SS table. I think that's referred to as the SS table.
Why is the data scattered? Like, because it's only append only, so shouldn't it be in sequence?
I mean, it's in sequence, in the time sequence, not in the key. Like when you want to look up some key, right? Now you have to go through O of n, through the entire segment length to find your key.
Got it.
Yeah, so that's the optimization they do, is they kind of sort the key. Yeah, so I think once because all the segments are independently sorted, so you can do a merge sort, right? When the compaction happens, merge sort algorithm is used to come up with the final segment. Go. That's the summary. Yeah, I'll be back. My son is, yeah, you guys go ahead.
Okay. All right. So let's see here. So that was a good summary. So we did leave up to the SST area. And this is kind of like what we were talking about. How do we make sure that the keys are sorted in the first place? Because we don't want to have ON lookups for keys. So a sorted structure on the disk is possible with a Btree, but in memory it's easier. And so we talked last time towards the end about red-black trees and AVL trees and how like those trees are optimized to have a balanced structure. So searching is faster. So if you use a data structure like a red-black tree or AVL tree, like that backs, like your SST, right? Then when a write comes in, adding it to an in-memory balanced data structure for red-black, for example, a red-black tree is sometimes called a mem table. So I should highlight this actually here. When a mem table gets bigger than some threshold, typically a few megabytes, write it out to disk as an SS table file. And this can be done efficiently because the tree already maintains key value pairs sorted by key. The new SS table file becomes the most recent segment of the database. And then while the SS table is being written to disk, writes can continue on the new mem table instance. So that's kind of like the main part here is like there's this mem table, it's backed by a tree structure, usually a red-black tree. And then, as the mem table gets big in size, then you write it to disk. And then this helps keep the key value pairs sorted. So from here, in order to have a read request, first try to find the key in the mem table, and then go to the recent on disk segment, and then in the older segment, and so on. So this is how you do your read operations. And we'll just highlight this part too. From time to time, running a merging and compaction process in the background to combine segment files and discard some overwritten files. So this scheme works pretty well, and it suffers only from one problem: database crashes. So usually what they do in the background, in addition to having this tree and the algorithm to read and write, they also have one more file, which is a log, and that is just to keep track of everything in case, you know, the system needs to reboot and restore the mem table after a crash. So every time this mem table is written out to a SS table, then the corresponding log can be discarded. So that's really the heart of it. Like an SS table is just a different way of handling the memory. And in the previous example, we were using a hash table. And the hash table didn't really have that great order. But when you think about order and you want to have better ordering with your keys, then it may be time to use a tree as a backing structure for your mem. And then from there, it's easier to look up key and values. And then you can run compaction and so on in the background. And then they also just have a log in the background as well to help if the mem table crashes. So beyond that is this LSM tree, and that just stands for log structured merge tree. Basically, this is the algorithm that we talked about just before is essentially what makes LevelDB and RocksDB and key value storage engine libraries for you know, other applications. So let's see here. Points are that like LevelDB.
So the basically the Elasticsearch search engine is based on this this algorithms, right? The log structured merge tree algorithm. So, yeah. So it's basically I think we discussed in the past that they maintain this reverse. So at a high level, what they do is they do this inverted lookup, right? Where we store the words and then their documents where it is stored. And then we, I remember, so we have this, it also does this background, it also has this background worker, which kind of keeps the indices. It maintains different indices for different I think keywords. I forgot. So do you have that? Can you share the Notion doc that we had? We had a picture there, right?
Yeah.
So
were you talking about mine or yours?
No, the Notion. Yeah, I think the mine thing. You know, the one that I shared. I had shared it last time. Let me bring it up. So I'm just trying to put the older, you know, knowledge we had just in context to see how this new information can be fit into that.
Yeah, I don't think I have the link, but let me
share my screen for
okay,
a
sure.
moment.
Okay, so you have co-hosting ability now.
Oh, okay. How do I? Okay. Participant, multiple participants share simultaneously. Advanced. Okay. This one. Okay. So we have this. So the way it is written is this, the tokens and the frequency and the document ID is the this is the actual index, and then we merge. Incremental indexing is since new indices are smaller and old indices are longer, we merge the small index into a large one. So
yeah, I see it. Okay, so this is kind of like how they do their side of the search, right? This is here's his document, then there's the
So essentially,
tokenizer.
yeah,
Go ahead.
essentially what happens in an LSM tree is like, while as Amulya mentioned before, it doesn't sort and write, but when it writes, like, it makes sure, this is the concept of like the whole concept, like, if you will, sharding. What it does is like it allocates in different nodes because it's a distributed system, rather than writing a particular set, like just an example, right? Maybe employee ID 1 to 50,000 will write in node 1, and from 51 to 100,000 maybe, right, or 100,000 it'll write to node 2. So that way it distributes the data. And if you recollect, in the distributed systems, there are some distributed systems which are leaderless. We'll talk about that in a bit, but that's why there is leader election. So when you go query a particular thing, it will like know from the master or the leader, right? It'll send it downstream to the data nodes, where it knows that those keys exist. So it helps you to faster lookup. At the same time, the data will get replicated and be redundant, in the sense the same 1 to 50,000 is there, the copy is there, and more than I would say in a 5-node cluster, it will be there in 3 nodes, so that, like, data is not lost. So there is a concept of quorum. It does leader election, and there is quorum calculation where it goes and replicates in different databases.
So, okay. Yeah, I think that's all orthogonal design aspects, right? So I'm thinking, so in this particular case, so what they're doing is they have, so in this, at least the document, what they're saying is they have this, the index is written to is, so is this, how are these indices made in the first place? How are they initially constructed?
So it's constructed with the hash, right? Remember that every, let's say a MongoDB or even in DynamoDB, there is an ID that gets generated for every record or document, right, in an LSM-based tree. So that hash defines, and that's what is used to index and store. And then later, administrators, sometimes they come and shard it, like in the sense you can change that a little bit, where you say, okay, this set, like, store here, and that's it. That's the whole concept of sharding by these administrators, where they can rebalance in a particular cluster those keys, saying, hey, you know what, like my database has gone too big. I want to add few more clusters, and then you do the rebalancing of the whole keys, the set of keys, right? The buckets that resides.
Yeah.
Okay. And the deduplication also. So, and you said the duplication also happens in order for the redundancy purposes.
Yeah, because remember I said, like, let's say 1 to 50,000 keys, right? An employee ID keys, let's say, if resides in node 1. For whatever reason, think of it this way: if node 1 goes down, then you lose those keys, right? And the storage. So that's why what it does, there is replication happens behind the scene, right? Once it's written, the replication happens in some database asynchronously on other nodes. So the transaction is not, any transaction you're looking up is not, like, affected, or on the database itself. That's why if you see these databases are eventual consistency. Sometimes, let's say co-location, now truly geolocation, right? You are in some Far East or wherever, and you're trying to access that. Reads generally will go to the nearest node as much as possible. Writes will always go to the master node or the leader, right? So once it's done on the log, so it's done. That's why these are like faster writes. It just writes it into the log and then forgets it, and then the database takes care of, like, making sure it just gets committed in the master log, and finding the right place to go and write it the first time in the node structure. And then once that's done, it kicks off the process. The leader says, hey, this is written there. And it'll send a ping, this thing to the other nodes to say, hey, now it's time for me to replicate this data. So these things all happen behind the scene, database property itself, right? We don't have to take care of that.
Yeah. So this is before we move away, you mentioned that the data is kind of copied over. It's kind of written to the master node and kind of copied over to the child nodes, right? So is it fair to say that the data is like the entire keys are kind of copied over to each cluster? It's like not like each one has its own version of the database, each node?
Each may have, depends on, again, the cluster size, how many nodes are there as part of the cluster. Let's say in a 3-node cluster, the quorum is 2. So which means at a minimum, your data will be replicated to 2 nodes, right? Over replication itself is another problem where you'll run out of space, right? Like you don't want it to be lying, let's say if it's a 5-node cluster, maximum, that's what the quorum calculation is. It'll say, okay, this data is available in 3 places. Okay, I'm happy. Let's say one of the node goes down, which so it becomes 2. So database knows that it has gone down. So at that point, it will replicate into another database. So that quorum calculation is okay to maintain 3 sets of the same data across any nodes, right? It may not be on the same node. Now again, right? It's a database property. It'll manage it and it'll go write it.
Okay. Yeah.
But the writes always happen in the log in the master, right? And then from the log, it gets committed because master at that point knows, okay, it has a measure of, okay, these indexes are all here. And all of a sudden you're like coming and writing something 4,000 entry, right? Employee entry. It knows, okay, I need to first write in this particular node and then replicate it across. Now, again, writing into that node, whatever it's able to get to quickly, it'll go and write of the 3 that's available, right? So there is no concept of saying, oh, I am the owner of this particular data of the 3 nodes. Anyone can be the owner. All 3 can be the owner based on how the database thinks is more optimized to do it.
Yeah, and the algorithm to choose which nodes to write what data into, I think that's another topic.
Yeah, that's a different topic itself. That's why these databases are so complex, right? In a way, thankfully, they are complex that we don't have to deal with it. It's like abstracted. Otherwise, it's like I wouldn't have a job. But the point is, it does way too much that sometimes. That's why I was going to say, when you said, like, is it really important, this section? I think it's really, really important to understand this section because if not anything, right, I'll tell you, interview for sure. This is a very strong case. I'll tell you my personal experience, right? When I was coming into AWS, so of course, I'm not a database specialty, but a topic when it came, when I discussed this, like, I think that kind of helped me, definitely. The guy interviewed said, I don't know, strong hire. I could be just, BSing it, but...
Yeah, it's kind of high level, so you could just be hand waving stuff. But yeah, so it's good to know the low level details. So coming back,
you can play around this with on your local machine itself with Cassandra with a 3-node cluster. See the logs. You can sort of like really look into this, how this all internal works. There are some tools where you can look into Cassandra where it writes into the logs. You can look into those storage logs and see, and
So coming back to like, okay, let me stop the share. I think what we were at is that log structured merge tree implementation in Elasticsearch, right? So so this is a different level of this basically the keeping the key values in the memory. So this is a different layer of abstraction. So I think what I was sharing earlier is a different layer of abstraction where the keys are basically written to and they're merged for easy lookup later. But I think I'm trying to understand, is this that do these two algorithms coexist, or is there a customized algorithm that Elasticsearch is putting in place?
So there are two paths to it, right? Like, let's go back to databases itself. Every database has a storage engine, right? Storage engine is different from the database. Database is a big package. Storage engine, think of storage engine as like just a simple writing into a file and managing that file on a hard disk or a flash disk. Right? Every database has write amplification, read amplification, and the space amplification. I know you guys are talking about log n most of the times, but that is only on the space amplification. That's why there is read amplification, write amplification. It depends on what kind of a storage you're writing to, flash or hard disk and stuff like that. But again, Elasticsearch is a different beast. One, it uses LSM just for storage purposes, right? On top, you have Apache Lucene, which does search and indexing. That is
exactly. So that's what I'm trying to wrap my head around, because the way Lucene does is it kind of has its own index, smaller index, and then it does its own merging. So this is happening at a layer above this compaction, this keeping the keys on available for easy lookup. So there are
it is happening not at the storage engine. There are two levels operating here.
Yeah.
Right. The search and index level on the Lucene that does a different algorithm which does its own thing.
Yeah. Wow.
It's pretty complex. Elasticsearch itself is pretty complex. And always you can go ask any administrator or even system they have put in place. Elasticsearch is always a growing pain. You have to constantly watch it. You cannot just let it go and operate it in a self-healing mechanism. You have to constantly shred. You have to add nodes, space. You have to constantly keep doing some administration on top of it. It gets complex because it's having too much data in it. And we want to store that log data for whatever reason, right? Governance, compliance and stuff.
Yeah.
Yeah. Like they say too in this chapter that Elasticsearch is more complex than key value, but I think they get to it later in the chapter. And I think that can be like a system design question itself for an interview. So I've seen like courses on Elasticsearch itself, like on Udemy and YouTube and all that. So I would highly recommend, after kind of understanding this section, going and checking that out, just to kind of get a better understanding.
Actually, that's what we are trying to tell. There are actually two different design systems. So basically, it just so happens that they're both. Lucene happens to have a key value index at a high level and a key value storage system underneath it. But the way they are used at each layer are completely different. So we have different algorithms operating at a higher level and different algorithms happening at the storage.
What Lucene generally does is mostly in-memory index is driven by them, right? It has in-memory as well. And anything that's not in-memory, it will piggyback on the storage kind of a LSM tree algorithm, right? Because it anyways has to go look up the storage. But in memory, what it does, it indexes as much and keeps it in memory. So that uses a different algorithm altogether, right? It brings in caching and all those things.
Mm-hmm. So you said that was a very pretty heavy. I don't know if I'm slow at grasping it. Can you repeat that, Karthik, once more?
No, think of it this way, right? Very simplistic API, right? API is there. We have caching as well enabled, let's say with Redis. So what happens when somebody is read queries constantly is being done? We look up the cache, right, till it gets invalidated, right? A very simple mechanism. And whatever things are not in the cache, or it's invalidated, or it's not even available in the cache, we go to the primary source of truth, which is the database of any sort. Same concept at a higher, in a distributed complex level. Let's say what Lucene does is like, it doesn't rely on the storage indexing on the disk, right, using LSM, but it abstracts it and has some information in memory, right, like a caching layer of sorts within itself, right? So that in memory also has to be indexed, because like it's a multi-node system, distributed system. So when queries or logs are being constantly whatever queries are being run, sometimes it runs it in memory, distributed in memory. Think of it like a Redis in itself, right? Actually it's not Redis, but just for sake of so in memory indexing and sharding, there's sharding happening as well, right? Because it knows the same kind of a structure, but it's not really LSM. It's a little more complex than LSM. That is done by Lucene, right? In memory. Any data that's not in memory, it will go to the storage engine, which will piggyback on the LSM tree at that point. Does it make sense? Or
okay, so you're saying the way it is written to disk is managed by this LSM algorithm, but what happens in memory is its own custom implementation.
Yeah. And again, it depends. The discussion goes back to how beefier your machine is, how much memory, because Elasticsearch are all not CPU dense. It's more memory dense kind of a system, right? Because it does a lot of in-memory caching and stuff. So of course, CPU is also needed. It's not like you need to have bare minimum, but the point is they are more memory intensive distributed systems.
Yeah, good discussion. I mean, it needs more pondering, but thanks for clarifying, Karthik. I will kind of wrap my head around it, and maybe if I get some clarity, I'll also next class I'll kind of explain my understanding.
Yeah, actually, there is a very good broadcast. I'll ping you internally in Amazon this thing, so you can look it up. It's a pretty good write up here. Yeah,
you could put in the WhatsApp chat. People who are interested can.
Yeah, but I don't think these guys can access it.
Oh, okay.
Internal Amazon broadcast this thing.
Oh, okay.
Yeah, I'll ping you there.
I mean, like if you find something similar to, then
yeah. If it's something is external, the whole thought process of how they did Elastic Cache managed services internally in Amazon. There is a blog that's written, and yeah.
Okay, good. Okay, then not to derail. Let's get back.
Okay. All right. So essentially, like the key points, right? I think so far have been that these are engines. They manage like how the data is getting saved, and then the key values are being backed by trees in LSM. So that's kind of like the main idea here. The LSM algorithm can be slow when looking up keys that do not exist in the database. So this could be an area of optimization. Like first you have to check the mem table, then you have to check the segments all the way to the oldest before you can be sure the key does not exist. So to optimize for this kind of access, you can use Bloom filters. And a Bloom filter is a memory efficient data structure for approximating the contents of a set. It can tell you if the key does not appear in the database and thus saves many unnecessary disk reads for non-essential keys. So reading is still kind of like an issue, like even though writing, is a little bit faster. And then there are different strategies to determine the order and timing of how SS tables are compacted and merged. The most
Does
common
anybody
options.
know what are Bloom filters? I mean, I have to say, yesterday was the first time I read about them.
Bloom filter.
A Bloom filter. Anybody knows? Or we can just study up and come back prepared next. I was reading up about it, but I didn't go to the actual implementation. It's a probabilistic data structure. So you get a 100% confident answer when the key is not present in a data structure, But when you get a positive answer, there are basically false positives. So when the Bloom filter comes back that a certain key is not present, then you can trust it. You can say that it's 100% not there. But when it comes back with the positive answer, there is a chance that the key might still be present. So it's kind of that's why it's called probabilistic data structure. It doesn't give you a Boolean answer. So, but I don't know how it exactly works.
Yeah, I think even this chapter here doesn't really go into a lot of detail about the Bloom filter, but this is good. You know what? I can put a link to this in our chats that we've been having so far, if you want to just kind of get a sense of it. I think you're right. It's kind of like it's used to speed up answers in a key value storage system. Values are stored on disk, which has slow access at times, which we discussed. Blue filter decisions are faster. However, some unnecessary disk accesses are made when filter reports a positive in order to weed out false positives. So
yeah. So when you get a when you get a positive answer, you are in trouble. You basically have to go do the lookup yourself again.
Right.
So it's say they say it's it is kind of for use cases like when you're signing up to see if your username already exists in the system, right? So I think that's a use case where they use Bloom filters. It's a pretty common data structure. Might never heard of them, but yeah.
Okay, we'll come back to it. It's not a big deal. Like for the most part, it's helpful for approximating the contents of the set. And there's other strategies as well. There's also this size tiered and leveled compaction. Basically, like if you use any of these databases like LevelDB, HBase, Cassandra, they're all kind of using some version of this optimization for compaction. In a leveled compaction, the key range is split up into smaller SS tables and older data is moved to separate levels, which allows compaction to proceed more incrementally and use less disk space. The basic idea, though, of an LSM tree is keeping a cascade of SS tables that are merged in the background. Data is stored in sorted order, and you can efficiently perform range queries, scanning all keys above some minimum and up to some maximum. And because disk writes are sequential, the LSM tree can support remarkably high write throughput. So the LSM trees are pretty good for writing. Yeah. And they are easier to search through for keys. So these are kind of like some advantages of an LSM tree. But, like in modern times, I think most things are backed by the Btree, right? Which is a different, different kind of structure itself for indexing.
Yeah. So with the LSM tree, writes are super fast because it's only append only, right? And any background compaction, any compaction happens in the background. So that's why the write is optimized, but the reads are there's an optimization they made to make the reads faster, which is to keep the key sorted, but still you still have to go through however number of segments that you have in your machine. You basically have to go through each segment, and you have to kind of do this binary search kind of an algorithm to find if you have a key in there, so the key that you're looking for in there. So it's kind of not greatly optimized for reads. I think that's where Btrees shine. They have a good read complexity.
Yeah, correct. So they're pretty much like the standard in all relational databases today, right? And a lot of non-relational databases use them as well. So I think this is what SQL probably has. And it says that Btrees keep key values similar to SS tables sorted by key, which allows efficient key value lookups and range queries. But then they have a different design philosophy. Basically, they break databases down to fixed size blocks or pages, traditionally 4 kilobytes in size. So I was just gonna say, like, this is, just so we know, like, this is 4,000 bytes. Read or write 1 page at a time. And this number will probably come back into like, why is it 4K later in this chapter. So I just wanted to point that out here. Each page can be identified using an address or a location, which allows one page to refer to another, similar to a pointer, but on disk instead of memory. So the concept of memory is kind of like not there. It's more this tree that is kind of like breaking the database down into blocks. And so here's kind of like a diagram. If you want to look up, a certain key, there are these pointers. And if your key is like, 251, then you'll first go through the Btree and then look for 251. You'll find that it's not in this column, so you'll go down to this column. And you can see this kind of looks like a tree. So 251 is on this side, the greater side, and then it's somewhere in here, and then that will point to the actual area in the disk. And so they say that, I think there was like a line here that basically said that it's kind of like, if you remember like a record, right? If you know like where the information starts, then the record will like point directly to that, item on the disk, and then, immediately read. So this helps, right? Like, this is a log n kind of flow to getting to the read. So it's a little bit faster.
So every read will take a login. So it is almost like a constant login. So there is no best case or worst case. It's always login.
Right.
Because the data is in the leaf node. So if you want to fetch the data, you have to go to the bottom. So it's basically you have to traverse all the levels. But yeah, it's almost constant for a given. Yeah, it keeps increasing. Of course, the levels keep increasing as you keep adding data. But whatever is the branch, whatever is that level that you have at all the reads will take that much. So many traversals.
Right. And let's see here. So I think we talked about this part, but yeah, I'll just read it here. If you're looking for key 251, you need to follow the page reference down this tree between the boundaries 200 and 300. That takes us to a similar looking page that further breaks down the 200 to 300 into subranges. Eventually you get to the leaf page, which contains the value for each key inline, or contains references to the page values where they can be found. And so this is called the branching factor. Like, the number of references to a child page in one of the pages in the Btree is called the branching factor. In this example, this example 3.6, the branching factor is 6. And then in practice, right, like, the amount of space required to store the page references and range boundaries can be typically several hundred. So there was, let's see here. If you want to add a new key, you need to find the page whose range encompasses the new key and add that to the page. If there isn't enough free space in the page to accommodate the new key, it is split into 2 half full pages, and the parent page is updated to account for the new subdivision of key ranges. So this is kind of like how the tree gets managed in the background. And here's another diagram where it shows you like growing the tree by splitting a page. So when we add this key 334 goes here, and then we split the page into 2 sections, and so 337 goes this way. And the reason they do the splitting is just to keep the tree balanced. And that's kind of, again, like the whole idea of like the balanced binary search tree. A Btree with n keys always has a depth of O log n. And oh yeah, this is why, like, I pointed out that 4 kilobyte thing earlier. a 4-level tree of 4 kilobyte pages with a branching factor of 500 can store up to 250 terabytes. So that's why this number is there. And this is why like it's a pretty good number, because, you know, like you can handle most cases for databases. That's a lot of storage, right? 250 terabytes.
So adding to what Amelia said, log n, I think that is if you are doing a single query on a table, but the minute you do add indexes, it becomes n log n, right? Or instead of on, it becomes n log n, because the complexity of the tree traversal just increases across tables, right?
You mean adding if you add indexes, then you just go look up in that index, right? Index
that is on a single table. Even though you have indexes, it is like if you're doing joins, right? Your on becomes n log n because it just increases.
Okay.
Yeah, because of this NKeys with the depth of log n, right? Is that what you're referring to, n log n right here?
Yeah.
Yeah, I think what Karthik is saying is like if you have multiple, if your query requires multiple table lookup, right? Then you would basically do this log n on n tables that you're joining on. Then it would be n log n, right?
Yeah, and that makes sense as to why, like, when you do these join statements in SQL, it takes much more time, right?
Yeah. But then also the branching factor also has to contribute to the complexity, right? So if you have a branching factor of 500, you basically have, at that point, maybe you do the, so how, like, let's say you have a 500 nodes, 500 data values in a single level, right, that you're looking at. How do you figure out your reference, right? There are so many 500 references in that. So I think you probably do binary search at that point. So it's then it's another login, right? So yeah, I mean, levels wise, depth wise, you have only like whatever the levels. If it is 4 level, yeah, that 4 is the 4 is your max number of pre-traversals. But within the node, you have a 500 branching factor. Now you have to figure out where in that branches is your branch, right?
Yeah.
So that again probably is probably they do it by research. It's not written out here, but I think that's what they do.
Yeah, I think we're getting ahead of ourselves too. Like, I think let's just kind of think about like the basics for now, and then we can come back to like scrutinizing it. But yeah, you know, I think everybody kind of has the basic idea. It's a tree that, you know, has to be balanced. Login lookups. There's no hash table. In pages as a concept, with the idea that you can store a lot of data, like 250 terabytes. The basic underlying operation of a Btree is to overwrite page disk with new data. And it assumes that the overwrite does not change the location of the page. So that's kind of important. Like overwriting does not change the location. All references to the page remain intact when a page is overwritten. In an LSM tree, which only appends and eventually deletes obsolete files. You know, so this version doesn't modify files in places, whereas the LSM tree does delete. So you can think of overwriting a page on disk as a hardware operation. So again, like here, this is what I was talking about, right? On a magnetic hard drive, this means that moves the disk head to the right place, right? And then waits for the right position on the spinning platter to come around, and then overwriting the appropriate sector with new data. In an SSD, right, solid state disk, what happens is a little bit more complicated in the fact that SSDs must erase and rewrite fairly large blocks of storage data at a time. But SSDs are typically a lot faster than spinning plates. So you get that trade-off in read and writes. Let's see here. So then
SSDs are don't perform too well if you have a write heavy operation, because the number of times you rewrite an SSD determines its life. So
Exactly.
if you write, since your Btree tends to have a lot of writes, SSDs happen to be a bad, kind of bad choice for Btree implementation.
Yeah. Yeah. I think
That's what they
that's
say.
probably what he's saying here. Yeah. So,
Yeah.
because you have to do this erase and rewrite. But again, let's we can analyze this too, like outside, and this might be a good thing to kind of go and look up just what's going on with SSDs versus magnetic hard drives with B-trees. Like here it says that if you split a page because an insertion was over full, this can be kind of dangerous. If the database crashes because only some pages have been written, you end up with a corrupted index. So this is kind of like a downside to some of the B-trees. But in order to make the database more resilient to crashes, B-trees have also a write ahead log called a wall, and it's called a redo log. This is an append only file to which every B-tree modification must be written before it can be applied to the trees itself. So this is their strategy for basically keeping the database and the resilient to crashes. When the database comes back up after a crash, this log is used to restore the B-tree. So again, like point is it's a tree that, you know, like also has this append log, you know, on the side, and that's how they'll bring it back. But it's not this in-memory hash table. It's more like a tree. And another complication of updating pages in place is that you need to like think about concurrency. And so if multiple threads are going to access the B-tree at the same time, you know, then you have to just basically, you know, do something like protect the tree's data structures with latches, which kind of locks, you know, the thread so that, you know, one can be read at the same, one at a time. Log structures are simpler in this regard because they just do all the merging in the background without interfering with some queries.
Yeah, it's a concurrency is a particularly painful problem with Btree because there let's say a write resulted in a you know, split at a lower level, right? And that could have a ripple effect, right? If that gets split, and then the upper the parent has to be updated with its new reference, and then if that is also full, then that also needs to be split, right? So it has a ripple effect. And if at the same time, if there is another write happening to a different node but in the same path, right?
Mm-hmm.
So
yeah,
basically you are in you basically, the other one is kind of in a bad shape now, so it has to wait until this all ripple things are figured out, and then yeah, we have to do some latching. And so sometimes, yeah, the writes might take longer than a simple write. It's not guaranteed that it will be fast.
right. And I think this is where the whole acid principles start to come into play, right? Like that's why like they make so much of a big deal about like you know, the whole atomic transactions one at a time. You know, if the transaction fails, they won't pretty much well, they'll redo it. They won't save it if it's a partial transaction. So this is probably like where that comes from. So I think they talk about it later in this chapter as well. So then this next section is all about like additional optimizations for B-trees. Let's see here. I think we've got 3 more minutes, so you can kind of go through some of them. But I guess like before I do that, does anybody have anything else to add? Because I feel like I read a little bit, but I wanted to just ask, you know, is the understanding pretty clear on what like an LSM is, what is a SST, what is a B-tree, you know, like how did their implementations vary, like which one, you know, is which one's more like modern, which one's more used, which one's more common. like what would you choose if you were gonna, write like your own, like from what you've seen so far, which one would you choose for a data engine?
I think applications, I mean, the kind of, that depends upon the types of applications, right? Like if your data doesn't, I think Btree is, like they rightly pointed out, right? Is a right solution for relational databases where it is optimized for read. And the log ones are essentially the log structured one, and I think is optimized for log kind of databases, right? Logs, so where you are capturing the events. So I think key value stores are better. I don't know if I'm right. Feel free to object to correct me. But I think the key value stores are better managed via log structured databases because they have this. They take advantage of this merge concept where like you are merging it's a simple key is expected to have multiple values, right? And then you kind of do the compaction. They have a whole elaborate set of algorithms to kind of optimize the duplicate keys and kind of keep the lookup fast for a key value kind of data structure. What do you guys think? I mean, that's my understanding, but yeah.
Yeah, I was just gonna ask like maybe Karthik or Akansha too, like, just in case.
No, I've not read this chapter. Just read the first 3 pages. I have to go and read today.
Okay, no worries.
Yeah. So as Mulya said, mostly think of like the use cases. Let's say where there is requirement for more consistency, like example, banking transaction, insurance, stock trading, all those things. There is a hard transaction limit where you want consistency properties, right? And everything.
Oh, Karthik, I think you're breaking up a little bit. Karthik, you broke up a little bit. Do you want to try again one more time?
Structures are mostly LSMs, right? Under mechanism is accessible, that actual algorithms, LSM tree-based structure. Case like the analytics, Btree, log, structure. I think ideal is hybrid both if you can afford in a big org. If you don't have that luxury, then preferably people will go with RDBMS because it's more reliable and less operational heavy, right? They don't have to think about the whole distributed systems, leaders, election, all those things. Keep things simple, right? From a KISS principle.
Yeah. Yeah, I mean, most of what you said, Karthik, there was a bad connection. So we kind of didn't, but yeah, I think we
heard the last part.
Oh, I'm sorry.
Yeah.
I mean, like I would say click analytics and all those things is all NoSQL based, but it depends on the use case. Ideal world would be hybrid of both if the org can afford, right? If they can't, mostly they go back to RDBMS because it's simple. It's not too complicated for them to have too many ops and etc.
Yeah, I think what I would suggest is like Akanksha, you go back, read, and then kind of ponder over, because there are like so many concepts that are applied at different levels, right? For you to, at the end of the day, as an application developer, if you have to choose a database, these concepts seem, fairly simple standalone, but like if you kind of put together, it kind of quickly spirals, right? So you have to kind of have that intuition as to be able to make the trade-offs and justify them when picking a database. So I think each one of us have to kind of, I think that's where notes taking helps. it kind of helps you zoom out and kind of pick the salient points and kind of make the right choice, kind of not give the knowledge in a nutshell, and kind of help you make the decisions quicker. So I know I've been doing bad job with the notes, but yeah. So I think I recommend, people to go and add. Don't wait for me. I although I have the good intention, like what Krishna used to say, good intentions don't work. So if people have the time, please go update the document, and so we all can benefit.
For sure. Yeah, definitely. I'll do that today. I'll look through it and I'll go through it.
Yeah.
All right. Well, I feel like, we got a little further again. We got some discussions that were pretty good. I think like going forward, it's just talking about like comparisons between Btrees and LSM trees, optimizations for Btrees, and then I think scanning ahead, like usually like I'd make my highlights like the second time I read. Let's see here. Yeah, like then it starts getting into SQL, and then we get into text search and fuzzy indexes. So this is kind of like a good section, and I think this kind of leads up into Elasticsearch. So we'll get there in terms of the Elasticsearch stuff. And then we revisit ACID here, and again, transactional processing. So we're building up to these concepts here. So these are good things.
We should take this opportunity to also pivot a little and then understand the Bloom filter concept, like how it works, because from like 5-minute read I had done, it seems to be a pretty common use case. Like for example, email signing up, right? You look up whether you want to know whether username exists already, and you have a big user base, you want a quick turnaround time. So I think it's a very common use case if you kind of think about it. So it has applications in many places. So I think it's worth, one of us can take that action item and kind of read up and explain to the rest of us. I will try to, for this time, yeah, because I started, I'll do it. But I think we should take those action items and come back and help everybody also kind of take advantage of the.
I'll read on Bloom filters.
You'll do that? Okay, nice.
Yeah.
Awesome. Yeah, that'll be great. Okay, well, I feel like we'll get through this chapter a little bit faster than the other chapter because there's still some to go, but I feel like we're getting closer to the end, so not too bad.
Quick question, and this is away from this chapter. If you're using Redis in real world in your application, will the Redis node always be separate from your application node?
Yes.
Will there always be a RPC call involved, because your application is sitting, whatever your code is sitting on one node and the Redis is always sitting on another node, or you can put your Redis node in the same place as your application node?
Okay, so you're asking whether it is a separate process or a separate instance, or is it running on a different host?
Running on a different host, because I'm talking about an RPC call. If there is no network call, then you are saving some bandwidth, right? So I want to understand when you are setting up Redis in production environment, is it always on a different node, or there are instances where you can set up Redis in the same place as where your application code is running?
It is run, from what I understand. I don't directly use it in my project, but I have a sister project where they use it. So from what I understand, it's basically a distributed in-memory database, right? So what that means is it's a separate process that's running on all your fleet instances, and they have to be in sync, right? All the instances have to be in sync. So it's running on all your hosts, just like your server is running on all the hosts. It's also running. It's again a different server running on all the hosts, and it has its own logic to keep the data consistent across all the nodes. So in order to answer your question, is there an RPC call that works to it? Yeah, I mean, it makes a call to a port, but that thing is running on your own machine. So it's not like an over the network call. It's basically connecting to a port on a different process.
Yeah, that
Okay.
makes the most sense to me.
To reduce latency, you can run it on the same, let's say it's an API server, right? API server of sort. So you can run the Redis on the same host itself. Traditionally, if you're in the path of having host-based mechanisms like EC2 or VMware kind of a machine, but if you go higher level into containers, obviously you don't run Redis the same container. It's not a best practice. So you'll run on different containers, and sometimes it can run on the same host. Sometimes it can run on a different host. It depends on your network hop as well within the VPC, how much of a latency is involved, right? Basic network latency. If the latency is like very minimal, you can completely run off in separate instances and still get away with the latency involved. If the latency is too high, yeah, obviously you'll run it on the same host. Cross region, in case of AWS, if you're running it on cloud, availability zone and region comes into play, right? You wouldn't want to run your Redis instance in a completely different availability zone, hopefully in the same availability zone to reduce the latency, hopefully in the same region. So all those principles come into play. So it all depends on a lot of factors.
Got it.
I know it's not straightforward answer, but because it's a little bit complex. Right?
But what is the point of, if it is running on a different machine, like what is the advantage? The main advantage of the using, basically the use case that it addresses is it's in memory, right? So if it's on a different machine, then it's not in memory anymore, right?
Yeah.
It's still in memory. Redis itself is in memory, right?
Yeah, it's on a different machine and in memory in that machine, but I want it to be in memory in my machine.
No, see, it's still, the transaction is still faster compared to querying on the database. The idea is to cache. The reason why those kinds of scenarios, I'll tell you, generally, those kinds of scenarios are people who want to use a shared kind of a caching layer where multiple consumers of that data itself are available, right? It's a shared. So if you size them isolated into your instances, others might not have access to it, or you might have to expose an API. Sometimes the needs are very different. So it could be a shared Redis kind of a structure for your org or for your business unit. So very different reasons that's driven, not completely engineering decisions, right?
Okay. Yeah, you can decide to run your Redis servers anywhere. Yeah, and then you kind of may but I think it defeats the reason I think it defeats the purpose is if you're making an over the network call. I think network is more unpredictable than discrete, right? So I think discrete, right? So I don't know if you're going to get the best out of the Redis. Whatever. Yeah, I think it's, at least in our implementation, the way we have adopted it is we have Redis servers running across all the fleets, and the servers that are running on all those fleets kind of takes care of keeping the data in sync, and we kind of connect to the local Redis server on the port. It's not over the network call, so it's still fast. Okay, I don't know if I answered your question, Akanksha.
Yeah, I got it. So I was discussing this with a teammate yesterday, and he said that he used an in-memory store because for Redis he will have to do a RPC call. And then I was thinking about it later on, that why can't he keep that Redis in the same node, and then that in-memory store that he's still using is sitting in the same host, so why not Redis? So maybe there are some tweaks over there. I'll have to ask him.
I mean, that's how we use it. Like it's on the same machine.
Yeah, maybe
Yeah,
just get
for
some information, you know.
yeah, for us it is not on the same machine for sure, because he said he'll have to do a RPC call and there is a network bandwidth involved. So
So when you say
Oh.
RPC, are you talking about GraphQL? Is that what you mean?
no,
Or-
not GraphQL. It's like it's a remote procedure call. You'll have to invoke from one node to another node. So
It's like
Okay,
a
okay.
HTTP call, but
Yeah.
different.
Okay. Just curious about that. All right. So maybe you can get some information from him and maybe share. All right. Well, good job, everyone. Good discussion as always. I'll see you next week, Wednesday. And in the meantime, just feel free to, discuss anything if you come upon it, because I know it's a pretty big chapter and there's a lot of stuff to go through. So looking forward to discussions. All right. See you all next week.
This is the most important chapter, to be honest.
Okay.
I would say like for another 10 years, if I'm attending interview, this is really important.
Makes sense. So we'll make sure we go through it very well. All right, Karthik. See you later. Bye.
I guess.